Big data promises to be transformative. The effective use of this data can not only deliver substantial top and bottom line profits, but also improve the performance of existing function, and also create opportunities for growth and expansion. Yet, very few organizations are able to reap these benefits, the main reason being the lack of the right infrastructure to handle big data, leading to poor data management and consequent loss of business revenue. One of the challenges that businesses face while delivering big data capabilities is the strain that it puts on their existing IT infrastructures due to the huge data influx and thereby slowing the systems. Businesses will need to invest in a more robust architecture that can handle the size and dynamic nature of big data. In this video, we will examine the different architectural considerations associated with big data and focus on the big data technology stack and its components. Let us first discuss the different architectural considerations associated with big data. To begin with, the architectural foundation of big data must take into account the functional requirements as well as the infrastructure requirements of big data. These will form the design principles that are critical for creating a strong environment that is conducive for big data. So, what are the functional requirements of big data? The architecture design must support the following functional requirements: capture data, organize the data, integrate the data, analyze data, act on the results of the analysis. In addition to the functional requirements, it is important that the architecture supports good computational power and speed. The architecture must also support the storage of huge volumes of data and also have the right amount of redundancy to protect from any unexpected latency and downtime. It must also include considerations for infrastructure software, operational software, management software, well-defined application programming interfaces, or APIs, and even software developer tools. Thus, big data management architecture must include a variety of services that enable companies to make use of a myriad data sources in a fast and effective manner. A framework of the big data technologies that can address the functional requirements for big data projects is referred to as a technology stack. Let us understand this technology stack in detail. The Big Data Technology Stack is a comprehensive stack that has several components that address specific functions of managing big data. These components are grouped in layers, where each layer performs a different function. These layers work on the big data in tandem to produce the desired results. These 8 key layers of architecture are: 1. Layer of redundant physical infrastructure. It comprises of the hardware and network elements. 2. Layer of security infrastructure. They enable data access, application access, and security of data. 3. Layer of interfaces and feeds to applications and the Internet. This is a blanket layer that provides a bidirectional access to all components of the stack. 4. Layer of operational database. These contain the database engines containing the collections of data elements relevant to a business. 5. Layer of organizing data services and tools. These aid in capturing, validating, and assembling the various big data elements in contextually relevant collections. 6. Layer of analytical data warehouses. These aid in the simplification of data for creation of reports and the visualization of data items. 7. Layer of analytics. This layer enables processing of data and providing a user-friendly representation of information. 8. Layer of big data applications. These hold the custom applications of big data that are relevant for the business. To meet these needs, various technical infrastructures exist today that facilitate big data, including cloud computing, virtualization, and the most popular big data technological framework, Hadoop. The Hadoop Distributed File System is an open-source project framework that enables a highly scalable, redundant data storage and processing environment that can be used to execute different types of large-scale computing projects. At the lowest level of the stack is the physical infrastructure, the hardware and the network. It is important to have some overarching principles to apply to your big data implementation. A prioritized list of these principles should include statements about performance. How responsive do you need the system to be? Availability. Do you need a 100% uptime guarantee of service? Scalability. How big does your infrastructure need to be? How much computing power do you need? Flexibility. How quickly can you add more resources to the infrastructure? Cost. What can you afford? As big data is all about high velocity, high volume, and high data variety with veracity, the physical infrastructure will literally make or break the implementation. Most big data implementations need to be highly available, so the networks, servers, and physical storage must be both resilient and redundant. The layer of redundant physical infrastructure can be split into 3 parts to understand it better. These are 1. Physical redundant networks. 2. Managing hardware, storage, and servers. 3. Infrastructure operations. The first part includes physical redundant networks. A business's networks should be redundant and must have the capacity to accommodate the anticipated volume and velocity of the inbound and outbound big data, in addition to their usual network. To this end, it becomes necessary to create physical implementations that are elastic. In addition, to cope with the ebbs and flows of network traffic, the infrastructure should offer monitoring capabilities so that operators can react when additional resources are required to address changes in workloads. Now let us look at the second part, managing hardware, which comprises storage and servers. A business's hardware, which is made up of its storage and server assets, must have sufficient speed and capacity to handle all expected big data capabilities. However, to achieve this, network performance must also be up to the mark. Finally, we will look at the third part of the layer of redundant physical infrastructure, infrastructure operations. Since optimum performance and flexibility will be present only in a well-managed environment, data center managers need to anticipate and prevent catastrophic failures so that the integrity of the data is maintained. After the layer of redundant physical infrastructure comes the layer of security infrastructure. Security and privacy requirements for big data have to be closely aligned to specific business needs. There are some unique challenges that arise when big data becomes part of the strategy. These include data access and application access, which mean that data and application access to data should be available only to those who have a legitimate business need for examining or interacting with it. A third challenge is data encryption. Encrypting and decrypting data usually stresses a system's resources, and this problem is magnified in the case of big data. To combat this problem, you can provide more and faster computational capability or identify the data elements that require this level of security, and only encrypt necessary items. Finally is the challenge of threat detection, which stems from the inclusion of mobile devices and social networks as sources of big data. As a result, it is important that organizations take a multi-perimeter approach to security. The next layer of the stack is layer of interfaces and feeds to applications and the Internet. This layer manages the feed of data into and out of both internally managed data and data feeds from external sources. Since big data relies on the fact that data from lots of sources are picked, this layer becomes critical for the big data solutions. Interfaces also exist at every level and between each layer of the stack. Without this layer, big data cannot happen. The next layer is the layer of operational databases. At the heart of a big data environment are fast, scalable, and rock-solid database engines that contain the collections of data elements relevant to a business. A choice has to be made between engines, or you could choose a mix of database engines, like Relational Database Management Systems, or RDBMSs. You also need to choose from database languages. For instance, you can choose SQL, which is the most prevalent database query language used today. Once you have understood what you need, what data you're gathering, where to store it, and how to use it, you need to organize it so that it can be consumed for analytics, reporting, or specific applications. This is where the layer of organizing data services and tools come in. This layer comprises of an ecosystem of tools and technologies that can be used to gather and assemble data in preparation for further processing. Technologies in this layer include a distributed file system, necessary to accommodate the decomposition of data streams and provides scales and storage capacity. Serialization services, necessary for persistent data storage and multi-language remote procedure calls. Coordination services, necessary for building distributed applications. Extract, transform, and load tools, necessary for loading and conversion of unstructured data. Workflow services, necessary for scheduling jobs and providing a structure for synchronizing process elements across layers. The next layer is the layer of analytical data warehouses. After the company sorts through the huge volumes of data, it is necessary that this information is provided to the end user in a user-friendly form. These data warehouses and data marts provide compression, multi-level partitioning, and massively parallel processing architecture for preparing the data that reveals patterns for analysis. The next layer is the layer of analytics. Existing analytics tools and techniques may not be able to work with large amounts of potentially real-time and dissimilar data. There are three classes of tools in this layer of reference architecture. The first is analytics and advanced analytics, which are tools that reach into the data warehouse and process the data for future use, like predictive analytics and sentiment analytics, for example. The next class includes tools that provide a user-friendly representation of the information from various sources, called reporting and dashboards. Finally, we have visualization, which allows business users to watch the changes in the data using different visualization techniques, including mind maps, heat maps, infographics, and connection diagrams. The next layer is the big data application layer. Although all the layers of the reference architecture are important in their own right, this layer is where most of the innovation and creativity is evident. Now we are seeing the development of applications that are designed specifically to take advantage of the unique characteristics of big data. These applications rely on huge volumes, velocities, and variety of data to transform the behavior of a market. Big data applications are either horizontal, meaning that they address problems that are common across industries, or vertical, which means that they are intended to help solve an industry-specific problem. The creation of big data applications will require structure, standards, rigor, and well-defined APIs. Now that you understand the big data technology stack architecture, let's evaluate your understanding so far. If you selected Security Infrastructure Layer, you are correct. The security infrastructure layer of the big data technology stack includes data access and application access. In addition, it also includes data encryption and threat detection. Let's do a quick recap of what you've learned in this session. The architectural foundation of big data must take into account the functional requirements and the infrastructure requirements of big data. The architecture design must support the following functional requirements: capture data, organize the data, integrate the data, analyze data, act on the results of the analysis. The 8 key layers of architecture are: 1. Layer of redundant physical infrastructure. 2. Layer of security infrastructure. 3. Layer of interfaces and feeds to applications and the Internet. 4. Layer of operational database. 5. Layer of organizing data services and tools. 6. Layer of analytical data warehouses. 7. Layer of analytics. 8. Layer of big data applications.